Now we'll start to touch on some of the geometry capabilities in GENDL. Base object is a primitive object type to give you a basic coordinate system. This consists of a length, a width, a height, the 3 dimensions in Euclidean space, and a center for the position, and an orientation on the 3 axes in space. Beyond this, we have GENDL functions. These take arguments for each vertex, because a base object coordinate system is considered like a box. You would have 8 vertices, 4 on the top and 4 on the bottom. 6 face centers, because a box has 6 faces, front, rear, left, right, top, bottom, and you have 12 edge centers. The edges are defined by specifying 2 faces, like front, top. There's an edge between those 2 faces. And finally, there's a face normal vector, which is a vector sticking out normal or perpendicular to each face. So there would be 6 of those. So all geometry primitives mix in base object, at least base object. And perhaps the simplest geometry primitive, of course, is the box. Box does not add much to base object other than its ability to draw itself in various formats. So here's the object we call a single box, inherits from base object. We give it some default values as computed slots for height, length, and width. And as a child, we have the actual box. So the parent is simply a base object. It has a single child, which is the actual box, which has length of the length, width is the width, height is the height. So it will be passed in, not inherit. Inheriting comes from the mix-in. Here what we have is passing in the values into the child object. Typically, the actual geometry will end up as the leaf level, just like we've done here. So you have a child object. It doesn't have any more children itself. So it is a leaf. And that's where the actual geometry lives in your tree. Higher level nodes might be a simple base object. Certain slots in base object are defined as trickle down by default, namely the length, width, height, center, and orientation. These are the basic 5 slots dealing with a coordinate system, and these are defined as trickle down in base object. So that means that for those particular messages, you do not have to pass them down to a child object. So we could write the previous example simply like this. Simply say type box, and automatically a height, length, and width will be passed down into this box. Now, other fundamental concept for working with geometry is points and vectors. Now, 3D points in GENDL are not first-class GENDL object. They're not defined with define object. A 3D point is simply a vector. It's an array. It's a Lisp array of 3 floating point numbers. And we have an operator called makePoint. A makePoint will take 3 numbers and will return a point object, which is really a vector or an array in Lisp. Notice each number, x, y, z, is converted into a floating point representation. Even if you specify it as integers here, by convention, 3D points do have 3 floating point numbers as their components. That allows certain math formulas that operate on points to be optimized because the system knows to expect floating point numbers for all the numbers in the point. Another way to make a point is to translate along vector. We have several other basic functions for manipulating points and vectors. But here's an example. Translate along vector, starting from make point 0, 0, 0, so that would be the origin. We want to translate along the vector defined by make vector 0, 0, 1. That would be a vector pointing into the z positive direction, otherwise known as the up direction, and with a distance of 10, essentially translating 0, 0, 0 straight up by 10 units. So you end up with 0, 0, 10. Here's a translate along vector 0, 0, 0 along the vector 1, 1, 1. That's going off at a 45-degree angle, a distance of 1. So you end up with this number. Other operators for manipulating points and vectors include rotate point, that works in radians. Rotate point d works in degrees. Rotate vector d, subtract vectors, add vectors, scalar times vector. And you'll find the definitions for all of these in the reference documentation. Something to note, in my experience, you're working in the world of mathematicians, you tend to use radians, so you would use rotate point. If you're working with engineers tend to work in degrees, so you would probably use the functions that end with a d, rotate point d, rotate vector d. Now we'll put a few of these concepts together and see how we can position a child object by specifying its center. So the center should be a 3D point, and as long as you're within an object definition, if you're within a defined object, you can use this translate, and translate will translate with respect to the local coordinate system in the object that you're defining now. And it accepts up to 6 keywords. You wouldn't use all 6 at the same time, but it respects these 6 keywords. Right, left, that corresponds to positive x, negative x. Rear and front corresponds to positive y and negative y. And top and down, top and bottom also is a synonym, corresponds to positive and negative z, or up and down, top and bottom.